Okay, let's talk about angular momentum. Anytime you see angular, that means we're talking about rotational stuff. But before we do that, let's go ahead and review over linear momentum real quick. And a few things about that you need to know that'll actually help you with angular momentum. Linear momentum is lowercase p, and p is equal to the product of mass times velocity. So therefore it depends. It's a quantity of motion. It's kind of similar to energy. It's the number one thing that governs car crashes and collisions and stuff like that. Now, units real quick, because the units are going to be the same for angular momentum. The units real quick, again, the English system is the weird one. The English unit for mass is a slug. So P is equal to slugs, and then of course velocity is going to be feet times seconds. We'll talk more about slugs in class and what exactly that is. It's an odd thing. To be honest with you, the SI system makes a lot more sense. P is equal to m times v. Well, mass is going to be in kilograms. Velocity is in meters per second. So it's kilogram meters per second. There's no shortcut in that. Now that is equal to a Newton times a second, because a Newton is a kilogram times meters divided by seconds squared. So if you multiply by seconds, one of your seconds cancel out and you have the same unit. So that's linear momentum. Now let's talk about angular momentum. Angular momentum is when objects spin. And if they spin, the type of momentum they have is very much similar as linear momentum, except when something's spinning, we have something called moment of inertia. The moment of inertia tells you how easy something spins. It depends upon how the mass is distributed and the radius out to which the mass is. And right now, we just can worry about that being a number. We don't have to go any farther than that. Now, for angular momentum, we're going to use the letter L. Capital L is what they use. And angular momentum, well, linear momentum is m times v. Well, since we're spinning, it's m times v times r. Is one way to do it. Now, one of the most common places we see, well, let's get to examples in a minute. I can also say L is equal to I times omega. I is that moment of inertia. And right now, I'm just going to give you the formulas in which you calculate it. The moment of inertia, it would depend upon the shape. Something like a spinning rod has a different moment of inertia than a spinning disc. So I'll give you the formulas on how to calculate that when we do the lab and stuff like that. And this is angular velocity or angular speed. So L is equal to I omega and mv times r. Both of those work together. And again, I will give you the formulas for how to calculate the moment of inertia. And again, right now it's just a number, nothing more. Okay, let's take a look at some common examples. One of the most common places we see this is an ice skater. And what happens when an ice skater, when she comes into her final turn, she does this. And then, of course, she gets skates in her feet. And so what she does is she starts herself spinning. So that means she has a set amount of angular momentum. And let's just go m times v times r. And then what's going to happen is she's going to tuck her arms. When she tucks her arms in, she's now going to look like that. She brings her arms across her body, like this. And now what's going to happen is she's going to spin faster. And we've all seen that. When they tuck their arms in, because now L is equal to m. Well, V's got to go up because R is going way down when she changes her radius as she does it. So key thing in review real quick. The two equations we're going to use are L is equal to I times omega, and then L is equal to mv times r. And you can use that again. This is something we will calculate, but there's no set formula for it because every shape has a different formula. So that this is rotational speed, which is going to be in rads per second. Again, can also be in RPMs, revolutions per minute. And if you get that, you're going to have to calculate and change that into rads per second. A nice review, though, if you haven't done it in a while. And then we'll do with this. We have a lab that involves this, in which we'll talk about spinning weights and changing it. We'll use strobe lights to measure the revolutions per minute of the thing, and then we'll calculate what I is off that. Anytime you see things rotating as they decrease their radius, they rotate faster. You see it in diving and gymnastics with people. Is a common way to do it. Also, again, as they rotate their body in, as they pull their knees in when they're doing some type of flip, they're going to rotate faster. By extending themselves and changing their radius, what they do then is they slow down. So that's how they can control themselves to do all sorts of flips and jumps and stuff like that. More in class.